Hello, everyone, and welcome to the Mindscape podcast. I'm your host, Sean Carroll, and I bring you bad news, namely that the world is going to end. Not the world as in the Earth that we live on, but the universe as a whole is going to come to an end someday. We don't exactly know when. And what I mean by an end, it might not be something as dramatic as literally the universe ceases to exist, but it might either change so dramatically that life itself would be impossible, or it could just fade away. The universe could end with a bang or with a whimper. So today I talked to one of the experts in this slightly depressing area. Mack is a theoretical cosmologist at North Carolina State University, also a very popular science communicator. Her Twitter feed is one of the top ones that fellow physicists follow. And we talk about the different scenarios that sketch out what might happen to the future of the universe. It's not something that we know about for sure, right? Making predictions is hard, especially about the future. But we know enough about the laws of physics to say what the range of possibilities seems to be. Either this sort of gently fading out, everything moves apart from everything else, and we just get colder and slower until the interesting, lively aspects of the universe just fade into nothingness. Or it could be something very dramatic. My favorite scenario that we talk about in this episode is the bubble of quantum death. If you're not familiar with what that is, it'll be explained to you in grisly detail. So this is both an educational episode in that we really do get into some real physics and cosmology, but also thought-provoking, that science has progressed to the point where we can actually say something about what the end of the universe might be like. Remember, if you want more info on Mindscape, you can go to the podcast homepage at preposterousuniverse.com/podcast, where you can also sign up to support Mindscape on Patreon if you want to get ad-free versions of the episodes and also a monthly Ask Me Anything episode for all Patreon supporters. So with that, let's go. All right, Mack, welcome to the Mindscape podcast.
Thanks. It's good to be here.
We're going to talk about the universe. It's a big universe out there.
Yes.
And I love the fact that you're writing a book about the future of the universe.
Yes. Yeah. Specifically the end, because there's so many books about the beginning. I felt like, we really got to cover the other side.
There are. And I noticed that, when you watch Cosmos and they have the calendar, right? The cosmic calendar. And the beginning of the universe is on January 1st and the end is December 31st. And we're only alive for a little bit at the end. Yeah. But I'm like, why does the calendar end? It should go on for a lot longer than that.
Yeah, definitely. Yeah, I mean, it's, it is interesting. Like everybody, you always get up to today, but I think people just really want to know about the future, where it's all going and stuff like that. And we just don't talk about that enough as physicists.
Well, and I think one thing to get right is the time scale. So let's talk about the part of the universe we know, the past, right? Because I think that a lot of people, when you talk about the future, the far future, they're thinking like 10 years.
Right, yeah.
So tell us a little bit about the size and scope of the universe as we know it now.
Well, so right now our universe is about 13.8 billion years old. And we know a lot about the beginning starting from like a billionth of a second, basically. And before that, things get a little murkier about exactly what was going on. But we have a really good map for how things have evolved up till now. And we're starting to get a good understanding of where things are going. But we can map out the expansion of the universe, and we can get a feel for the size of the observable universe, which is often used to mean the universe. But when we talk about the observable universe, we're talking about a region that we can see, that we can get information from. And that's pretty big. That's about 46 billion light years in radius, something like that. And that comes from just the fact that as the universe has been expanding all this time, there's a certain distance where if we tried to look farther away from that, the light from that part of the universe we're trying to look at would take longer than the age of the universe to get here.
Yeah, so we know what the age, when you say the age, even there, we have to be careful, right?
Yeah.
Because we mean the age since the Big Bang.
Yeah.
There could have been something before the Big Bang.
Sure, and the other thing I should mention is that when people talk about the Big Bang, there's a sort of public understanding of what the Big Bang is, and then there's the way that physicists usually use it, and those are not always the same. So if you talk to somebody on the street and say, what was the Big Bang? people say, well, it was an explosion where the universe started as a single point and then exploded out, and that was the Big Bang. And if you talk to a physicist, usually what we're talking about is something really different called the hot Big Bang, where what we're talking about is just simply the fact that the universe was hotter and denser and smaller in the past, and that just comes from the fact that the universe is expanding now and cooling, and so if we go back in time, we can dial that back, and we see that the universe was cool, hotter and denser and more compressed in some way, and that is completely incontrovertible. Like that like
the Big Bang really did happen.
That in that sense, the Big Bang absolutely happened, and we know that because we can see it. Yeah. We can actually see it directly, because if we look far enough in any direction, the light has taken so long to get to us that it's coming from the time when the universe was still completely on fire.
Do you know the name Eric Lerner?
Yes, sort of.
Author of a book called The Big Bang Never Happened.
Oh, really?
Yeah.
Okay.
Back in the day, even in my day, the 1980s, 90s, when I was in grad school, there were still people out there who just denied that even the hot Big Bang model was correct. Yeah, the plasma cosmology. You heard of this? Like, the most important force in the universe is electromagnetism, not gravity, and so forth.
No. Yeah, I hear about that on Twitter all the time.
So there's a certain amount of stomping out of myths that one has to do. But okay, the Mindscape official position is the Big Bang happened.
Yeah. I mean, the hot big, the fact that the universe was hotter and denser, in some sense smaller in the past, and we can actually see it. And one of the things I think is kind of neat is, the TV show The Big Bang Theory, the beginning of the theme song is actually really nice encapsulation of the Big Bang Theory.
Yeah.
The whole universe was in a hot, dense state. Nearly 14 billion years ago, expansion started. To stop there, that's the Big Bang Theory. That's
exactly right. It didn't use the word explode.
Nope.
It didn't say there was
a point. There was a point. No singularity. And there may have been a singularity. Like, it's possible that before that fiery state, that the universe was infinitely dense. It's possible that we get back to that point. But there's that fiery state was. We see the part that was about 380,000 years after the beginning. In the 380,000 years, a lot happened, and we don't know at the very beginning of that if there was a singularity. We think probably there was this rapid expansion, inflation, and what happened before that super rapid expansion in the first billionth of a billionth of a billionth of a second, we don't really know.
I'm only 50-50 on inflation myself.
Yeah. I mean, and that's also like, it's sort of the standard cosmology, but people have different models of that. So, but I should say that, like, that really is the, like, inflation, if it happened, was 10 to the minus 34 seconds, right? So we're pretty good from 10 to the minus 34 seconds onward, which I think is an amazing achievement.
It is certainly an amazing achievement. And but let's give the skeptics some evidence here. So you said that we can only see things that are past a few 100,000 years after the Big Bang, but you also said we have a very good picture of what's going on a second or less after. So how do you get from here to there?
Well, so there are a few things that we can do. I mean, one thing that is that we can look at the patterns in that background light from 380,000 years after, and we can learn something about the matter and energy content of the universe and the expansion history from looking at, like, really carefully analyzing those patterns. Another thing we can do is we can just extrapolate that the universe was hotter and denser, and we can do experiments that make hot, dense little bits of matter and energy and figure out what physics is doing in those situations.
Literal experiments here on Earth.
Yeah. So the Large Hadron Collider can smash particles together and reach these really high energies where the conditions would be very similar to some of the early universe stuff. There are colliders that can make quark gluon plasma, which is the kind of, like, precursor to the particles that we can detect today, and that's what we think the universe was filled with in this very, very early time. And so the fact that we can make a little sample of a Big Bang universe is kind of cool.
Yeah.
So there's that, and then there's also some sort of slightly more indirect evidence from, like, the abundance of elements. It's called Big Bang nucleosynthesis. So in this early hot stage, there was a time when the whole universe was as hot as the center of a star, and so it was fusing elements together and making helium and lithium and a little bit of other things out of hydrogen. And so we can we can figure out what the abundance of those elements should be in the universe if that were taking place, and it matches really well. And so there are a few things like that where we have a really good understanding of charting out all the steps from that sort of quark gluon plasma stage through the couple 100,000 years to the cosmic microwave background, this background light that we see. And then from there on, we have other kinds of observations.
Yeah, I think that it is, like you said, amazingly impressive that the human race has been able to do this. Like, I'm teasing Big Bang denialists a few seconds ago, but in the 50s, it would have been completely sensible to be a Big Bang denialist. And 100 years ago, there were no pro-Big Bang people. The idea that the universe is expanding hadn't been figured out. So all of this is the last century of human progress.
Yeah. I mean, I think it's neat that, it was during Einstein's career that we went from an understanding of the universe as being static to an expanding one. And it really changed the equations he was using to describe the evolution of the universe. And it totally changed our understanding of just how cosmic history worked and where we're going in the future as well.
Well, it's also a great example of the interplay of observations or experiments versus theory, right? So you mentioned Einstein. Einstein didn't go to any telescopes and collect any of this data, but he is the one who set up the framework that we use to think about the expansion of the universe.
Yeah, and of course he wasn't the first person to talk about some of these things. Lemaitre and there are a couple other people who were sort of putting together this idea of the Big Bang theory and the expansion of the universe and everything. But there's a kind of neat story behind. He was writing down equations that we still use to talk about the energy and matter content of the universe. And he put in an extra term in these equations to account for the fact that the universe appeared to be static, threw it out when the expansion started, and now we've been shoving it back in because we need it for another purpose, which I can go into that.
We definitely do want to go into this. I just want to make sure that the audience appreciates the fact that general relativity, Einstein's theory of gravity, is the way that we talk about the expansion of the universe. It's not just, we look and see it's expanding. We use Einstein's equations to run it both forward and backward in time.
Yeah. And that's another astonishing achievement because general relativity is like the most bulletproof theory out there. Like we throw everything we can at this thing, and we haven't found a single
I know I've tried,
anomaly. Like everything looks exactly as it should if general relativity is the law of the land and never violated.
Right.
Which is a little strange because we know that there has to be somewhere where that isn't true because quantum mechanics and general relativity tend not to work well together. So there's got to be something's got to give somewhere in there. I mean, maybe it's something about the interplay between quantum mechanics is there's a more subtle thing and they can both be right in their own ways. But it really has been amazing to watch, all of these tests of general relativity, everything you could possibly think of, and everything passes completely. It's all looks perfectly right. I mean, even, the gravitational waves from black hole collisions that LIGO has been seeing, there was a sort of a signal simulated with computers using general relativity, like what that signal should look like if these black holes collide, and the signal comes in and it exactly matches. It's like completely perfectly. There's no deviation.
Yeah, it exactly matches the prediction from some equations that Einstein scribbled down in 1915.
I know, it's
without
incredible.
Any modification or improvement, right?
Yeah. And we're just still like, it's like, well, that still works.
Seems to be nature. Yeah, I mean, probably breaks down like at the Big Bang or inside black holes, but in the universe we see, general relativity. There you go. Let me pause for a second to talk about Quip, QUIP, electric toothbrushes. I remember a while ago going to the dentist and asking what kind of dental floss was the best, and I was told whatever you actually use. And the same thing is true for electric toothbrushes. Not just that you have it, but that you use it and how you use it. That's why Quip was created by dentists and product designers to focus on what actually matters for your oral health, healthier habits using the toothbrush. Quip automatically delivers brush heads to you every 3 months, so you get clean new bristles all the time. It has a sleek, intuitive design that is simple to use and comes with a travel cap, so you can bring it around with you when you're traveling. The travel cap doubles as a mirror mount so you can see what you're doing. It's altogether a very modern approach to keeping your teeth in their best shape. Good habits matter to live a healthier life, so help form fresh oral health habits with Quip. Quip starts at just $25, and you'll get your first refill free at getquip.com/mindscape. You can both support the show and start brushing better by going to getquip.com/mindscape to get your first refill free. Getquip.com/mindscape. And so, okay, you hinted, I'll let you, tell the punchline to this particular thing. The universe is expanding.
Yeah.
We can map out its expansion rate. You already gave two hints about what we're going to talk about right now, because you mentioned Einstein stuck this extra term in.
Yeah.
But you also said the universe is 13.8 billion years old and over 42 billion light years across. How does this happen?
Well, that happens because, so you, in terms of the size of the universe, I said that the size of the observable universe is set by how long it takes light to get from, the beginning to us. And how far that could go. And you would imagine that should be 13.8 billion light years, right? Because light travels 1 light year per year, and we've had 13.8 billion years, and so that seems like it should make sense. But the universe has been expanding since the beginning, and so the point that where light has taken 13.8 billion years to get to us has been pushed much farther away now because of the expansion of the universe and the whole history of the expansion. And one thing that factors into that is the fact that the current expansion is going much faster than it seems like it should be, and this is something that has been a real revolution in physics since the late 90s. So one big question that sort of relates to the stuff I'm interested in right now about the end of the universe. One big question is, how is the universe going to evolve in the future? Okay, we know that it's expanding now. Is that expansion going to keep going forever? Is the expansion going to turn around and then we recollapse and have some kind of big crunch? Like, what's going on there? And so in the late 90s, they were trying to figure this out. And really what you need to do to figure that out is you need to figure out the balance between the amount of matter in the universe, the amount of gravity, energy in the universe, and how quickly it's expanding. It's sort of the same physics as if you take a ball and you throw a ball up into the air. If you throw it faster, it'll go higher up. It'll be slowing down the whole time, and at some point it'll fall down. If you could throw it at 11.2 kilometers per second, it would reach escape velocity. It would go off into space. It would not fall down, but it would always be slowing down a little bit as it goes, because that initial push is sort of countered by gravity between the ball and the Earth the whole time. So it should always be slowing down, but it might keep going forever, or it might turn around and come back. And so we were trying to figure this out for the universe, because basically entirely the same physics applies. You had this initial push to the Big Bang, and then from there everything's expanding, but the gravity is trying to pull it back. So we're just trying to figure out, is there enough gravity that it'll come back? So we wanted to know how quickly is the universe slowing down in its expansion? What's that deceleration rate? So that we could figure out, is it enough that it'll really turn around or not? And so they went out to measure the...
This was, by the way, this is the hot topic when I was a graduate student, right? Measuring how fast the universe was decelerating.
Yeah, the deceleration parameter,
Will it
Q0.
eventually turn back or keep on expanding just ever more slowly?
Yeah. And so they wanted to measure this deceleration parameter, and they went out to measure it, and they found out that the deceleration parameter was a negative number. They found out that the universe is not decelerating at all. It's accelerating. The expansion is going faster and faster. It was slowing down. So the beginning was really, really rapid expansion. Then it's been slowing for a long time. And then something like 5 billion years ago, it starts speeding up. And that's exactly as weird as if you throw a ball into the air and it goes up for a few feet, sort of slowing down, and then just shoots off into space. It's the same weirdness, in terms of this does not work with our regular physics. And so that was a big mystery when that was discovered. A lot of people were not sure if that really works, what was going on. And I mean, you were active in the field at the time, so you remember. Yeah. But it turned out, everything seemed to be fitting with an accelerating universe. And so we had to figure out how to make the universe expand faster. And it turned out that little term that Einstein had put in his equations at first to just keep the universe stable, because he thought that the universe was not expanding, but there's all this gravity, so he had to have something to kind of balance that gravity out. He put that, so we put that back to balance the gravity out and overcompensate and push galaxies apart from each other.
Yeah, the cosmological constant or the vacuum energy or whatever you want to call it.
Yeah, the cosmological constant. We usually write it as a lambda term, and that's so that's we're stuck with that now. Like we don't know if it's a cosmological constant or not. There are different kinds of what we call dark energy that can do this, that can make the universe expand faster. So it may be that the dark energy is a cosmological constant. It may be something that changes over time in a different kind of way. But we call it dark energy because we don't know what it is and we can't see it, but it's making the universe expand faster. And you have a better name for it, right?
Yeah, I tried to call it smooth tension because tension is a negative pressure, and that's really what it is.
Yeah,
but, you know, like all my great ideas, they're before their time, frankly.
Yeah. Your genius has not been recognized in
It
this
hasn't.
matter.
I'm trying. But so we have the fact that the universe is accelerating. We can explain it by imagining this vacuum energy or cosmological constant or smooth tension, which has the property that it's the same amount of energy in every cubic centimeter, even as the universe expands. But as you're saying,
which is super weird, I should point out.
Like, super weird.
That's super weird because you normally, you know, like the density of something will change as the size of the box it's in gets bigger. You know, you have a box and you make it twice as big, you have a lower density of whatever was in the box. And dark energy isn't like that. You make the box twice as big, now you have twice as much dark energy. Like that's, I mean, everything about this stuff is weird.
Well, let's be specific about the kind of weirdness.
Yeah.
It's exactly what the theory predicts.
Yes.
Right? It's just weird to us, to our experience.
Yeah, because we've never encountered a material like that.
Yeah. I mean, I do, it rubs me the wrong way a little bit. I think that people overemphasize the weirdness and mystery of the cosmological constant.
Yeah.
Like if it's there, it just makes perfect sense. Yeah. We understand it perfectly. It's not some ineffable mystery. Why it has the value it does is a mystery, but its nature is not.
Yeah, I mean, it matches with the equations. I guess when I'm talking about the weirdness, I mean that nothing in our experience on Earth or in any other kind of experiment does what the cosmological constant does.
Absolutely, that's true.
Yeah. And it is very similar to physics, to throwing a ball up in the air and having it shoot off into space for no reason. But on a cosmic scale, that's okay because of the cosmological constant.
So, in your opinion, as a professional cosmologist, what is the chance? What is your Bayesian credence that the dark energy is a cosmological constant versus something dynamical?
I mean,
because it could also be something that is almost constant but changing a little bit.
Yeah. I mean, you know, I feel like the data fit the cosmological constant so well, and you know, it's hard to like. It seems weirder to me that something would mimic a cosmological constant so perfectly without actually being it. But you know, I don't know. I don't want to put too much money on any particular thing there. But I feel like I go with the cosmological constant as the default assumption, and until I see some kind of evidence for anything else, I'll just stick with that.
I vary between 90 and 95% confidence that it's the cosmological constant.
Yeah.
Of course, it would be a world-shattering discovery. It was not, so it's very, very worth going to look.
Yeah,
but it probably is.
Yeah. But it's tough because there's not much we can measure about it.
No.
You know, unfortunately, it seems if it is a cosmological constant, it's just a property of space-time. Every little bit of space-time has this little push in it, and if you want to think about it that way. And so it's completely uniform over space. It's utterly invisible. All it does is stretch space. And so the only two things you can measure are the expansion rate of the universe and the growth of structure in the universe, you know, how galaxies come together. And that's it.
And
there
we've done
no
that.
other measurements. Yeah. And we've done those measurements and it looks exactly like cosmological constant. It's like, well,
yeah.
You know? I mean, there are, to be fair, some of the alternatives have laboratory tests you can do where you might be able to detect something cool in a lab. But if it is a cosmological constant, we're never going to see any spatial variations. You know, everything will look exactly like, you know, it's just constant density forever, you know, expands the universe perfectly uniformly. And that's it. And we'll just measure that more and more precisely.
Yeah. And the alternatives that you mentioned are, you know, high risk, high gain kinds of things. It'd be really, really important if they were true, but we don't think that they probably are. So,
yeah. But there, you know, I mean, but there are some big mysteries around the cosmological constant, which I think are important to talk about and maybe not talked about enough. Like the size of the cosmological constant, the amount of this stuff that's inherent in space-time is weird, right? Because when you do calculations about how much vacuum energy there should be in space, so how much the sort of intrinsic energy in every little bit of space should be, you get a totally different number. And that may be that we are terrible at those kinds of calculations, but it seems like it should be much bigger. Like the whatever the cosmological constant is, it should be much more effective than it is. It's just right now it's just this little bit of expansion. It's currently dominating the universe because the universe is getting really big and everything else is diluting out. But it's still like way smaller magnitude in terms of its effects than we think it should be based on other kinds of calculations. And so when we calculate, vacuum energy from quantum field theory first principles and compare that number to the cosmological constant, there's a massive disagreement.
Yeah.
And that's...
So the mystery is not that there is a cosmological constant, but that it's so small without quite being zero.
Right. Yeah. And so I think that's a really interesting question that maybe the point is that we need to better understand, the theory and, how that all fits together. But it's nice that there's something that we have that, we can say, okay, this is legitimately strange and we need to sort it out, rather than just like, well, this is what we expected, it's there.
And so many people have been driven to the multiverse and the anthropic principle because of exactly these reasons. So again, in your professional capacity, tell us what the truth is.
Well, so these multiverse ideas are I mean, there are lots of different kinds of multiverse. The one you're talking about is we have different vacua, different sort of regions of space where the cosmological constant might have different values. So we have our observable universe that seems really big to us, but it might be a smaller part of some much larger space where there are other sort of pockets of universe with different values of the cosmological constant. And it may be that ours is small just because if it were way too big, then you couldn't form galaxies. And so it has to be kind of close to zero, and it doesn't have to be exactly zero. And so we just happen to be in a region where it's not quite zero, but it's, sort of conducive to life. And that's the anthropic argument for the cosmological constant. I've never liked anthropic arguments. I think that it's entirely possible that, that we'll be forced into this at some point, that there's no other explanation, that it is just sort of an environmental effect. But it's never been appealing to me.
Okay, but I want you to give it a percentage. If you have a bet.
A percentage on the multiverse or a percentage on the cosmological constant is what it is because of
the anthropic principle.
Principle. Like 50-50 maybe.
50-50, yeah. I think that's fair. I mean, we know so little, right? It's just like, if tomorrow a preprint arrived with a really killer explanation for why the cosmological constant should have exactly its current value, people's belief in the anthropic principle would plummet.
Yeah.
So.
I mean, there are some things that have to be described anthropically. Like there are some, like the fact that we live on the surface of a planet and not in deep space or in the center of the sun, that's an anthropic thing, right?
Obvious anthropic explanations,
yes. But properties of the cosmos itself being anthropic, I'm less keen on those ideas.
We'll see. But okay, if the cosmological constant is the right answer to the dark energy, if it is something that is not changing as the universe expands, so what does that tell us about the future? What does the future of the universe hold?
Well, like the sort of standard picture of the future of the universe based on our sort of concordance cosmology is this idea that, we have dark energy, we have dark matter, which I guess we can talk about later, and we have regular matter, and the universe started with the Big Bang, and it's been evolving ever since. That points to a kind of sad, bleak future for the universe. So I mentioned...
Don't be judgy about the universe.
I mean, okay, maybe you can find this inspiring, but basically what happens is the universe kind of fades to black in this really long, drawn-out way. Because what happens is, I mentioned before that the cosmological constant is dominating the universe, because if you have a universe where everything else dilutes and this thing doesn't, then as the universe gets bigger, it's going to be a higher and higher percentage of the universe. And because every part of the universe that has cosmological constant in it is growing, it's going to make the universe expand faster and faster and faster. And so eventually, there will be so much space between galaxies that we won't be able to see other galaxies anymore. I mean, the caveat is that there's one heading toward us, and so that one will hit us. The Andromeda galaxy will collide with ours in about 4 billion years, and our little local group of galaxies will kind of coalesce into one big
We're
mess.
gravitationally bound to each other,
Yeah.
but the ones that are not bound,
Yeah,
just
the
like
ones that are far away.
baseball you throw up into the air,
Yeah.
that's going to go on forever.
Yeah. And so in something like 100 billion years, we won't be able to see other galaxies anymore because they'll be so far away and their light will be so stretched out that we won't be able to pick up any information from them. So extragalactic astronomy will be over.
But again, 100 billion years.
100 billion years,
So the universe is only
so
14 billion years old now.
Yeah. So it's a long time. And then, at some point we won't be able to see the cosmic microwave background anymore because it'll be too stretched out by the expansion and the energy will be so dilute from the light from the cosmic microwave background. So people in this very, very distant future will not be able to figure out that the universe had a beginning. Sort of cosmology will be very different and more limited.
It'll be a lonely little island of the universe, unless we were able to successfully send them records.
Yeah. But nobody will be able to check this stuff from first principles. And then as the universe keeps expanding, since there aren't other galaxies coming toward us anymore, you don't get all this like new material thrown into the galaxy, so you stop forming stars. You use up all the hydrogen in our galaxy with making stars. Then those stars die and sort of fade out, and then so eventually you have a bunch of black holes. And
how long does it take for the stars to fade out?
Oh, it's many, many, many hundreds of billions of years. I mean,
Okay.
some of these stars are very, very long lived. So
Yeah.
I don't know exactly, but you get many generations, and then they just
But
fade
eventually
forever.
you run out of fuel, right?
Yeah,
There's a
yeah.
stellar energy crisis.
Yeah. And then and then you don't make new stars, and then a bunch of things just start collapsing into black holes, and those black holes then themselves start to evaporate. So Stephen Hawking, one of the things that he worked out is that black hole, if you leave a black hole alone long enough, it will start to lose mass through particles sort of quantum leaving. I don't know how to explain it without getting into the details, but yeah, so the black holes will start to evaporate, particles will decay, and we'll be left in this cold, dark, empty universe, and that's called the heat death.
And that lasts for how long?
Forever.
Forever.
I mean,
for
that's
infinity years.
Yeah, I mean, but there is a sense in which at that point time stops mattering. So once you get to the real heat death, I mean, this is sort of, we're getting into your specialty, but we reach the maximum entropy state of the universe. So we get the sort of maximally disordered universe where all energy is just in the form of waste heat. And it's very little, I mean, it's called the heat death because energy turns into waste heat, but that waste heat is at a temperature of like 10 to the minus 40 Kelvin or something. Like it's very little
Incredibly
energy.
tiny,
Yeah. And then you have no structure, you have no order, and you just have like a couple of stray photons, and that's the maximum entropy state. And if you're at a maximum entropy state, you no longer have an arrow of time, right? So
nothing is happening in any interesting sense.
Yeah,
right?
yeah. So we define time by the direction where entropy is increasing. If entropy can't increase anymore, what even is time? And
So, there is time, but I think you said it correctly before.
There's
It doesn't
no
matter,
arrow. Yeah,
right?
yeah,
There's
it
no
doesn't-
arrow of time.
yeah.
There's no difference between one moment and another. It's
Yeah,
just the
yeah,
same
yeah.
thing.
Yeah. So you have this eternal state of this cold, dark, empty universe.
I used to think that because of quantum fluctuations, such a universe would not be completely quiet. There would be fluctuations in Boltzmann brains and even Boltzmann solar systems and so forth. I now think that was a mistake, and it was just bad quantum mechanics. I think the correct statement is if there were an observer measuring the quantum state of the universe, they would occasionally see fluctuations into brains and so forth. But there's not any observers measuring anything. There's nothing around. The quantum state just sits there quietly, unchanging forever and ever. I think that you're right. It's a real heat death forever. And that's the most likely one, right? Of all we're going to give our listeners a menu of options for the future. And do you think this is the most likely future?
I mean, I think this is the one that seems to be, best the most clear extrapolation from the data. You don't have to throw in any new physics. You don't have to extrapolate any of our current theories beyond the regime where they make sense. So in that sense, I think it's the most clear extrapolation. I'm not fully convinced by the argument that there are no fluctuations at that point. There's been some really interesting, cool suggestions that you can have a quantum fluctuation that creates a new universe, or that creates like just some moment in time from a current universe in a way that interesting things can happen. But, that is super speculative. We don't know, for sure what the best way to do quantum mechanics in that environment is.
No,
right?
I do think you're right. There's a footnote that I should have said in what what I just said, which is that if you can bubble off a completely separate universe, a baby universe, then those could continue to be created toward the future. And maybe we're even the baby of somebody else's universe.
Yeah. I mean, I feel like that's kind of cold comfort because we're still dead. You know?
We're dead.
like I still consider it the end of the
anyway.
universe. Yeah, but like I still feel like once our observable universe reaches a heat death, like that's it for our universe. Maybe some other universe will happen, but it won't be in any way connected to us. It'll carry no information from us, and so so it's nice to think that there's some kind of rebirth, but it has nothing to do with
It has nothing to do with us, certainly. There was this old paper by Freeman Dyson where he claimed that you could live forever in an eternal universe.
Yeah, so there's a caveat to that though, because I was just talking with him a couple of weeks ago actually about this. Because I've been talking to a bunch of people about my book. Yeah. And that only works for a universe that's linearly expanding. It doesn't work for an accelerating universe. And so he was kind of bummed that his idea doesn't work anymore. Because his idea was that if you are in a universe that's expanding forever and you keep like slowing down your processing and hibernating and stuff, you can technically live forever.
But it was always a cheat. It was still, you're just running your cycles more and more slowly.
Yeah. But I think it kind of gave him some sense of hope. And now it's like, well, no.
Okay, so it is weird. It's a weird human quirk, right? Even if we think that 100 years from now we will certainly be dead, part of us doesn't want the universe to die.
Yeah, it's really
quadrillions of
fascinating.
years from now.
It's really fascinating. And this is something I'm spending a lot of time thinking about writing this book because, there's this sense that if the universe is going to end, at some point we have no legacy. There's some point at which we stop having ever mattered.
The pointlessness of it all is really driven home.
Yeah. And so you have to think about, like, what does it mean? Like, how do you find meaning in life? Because some people find meaning in life through the fact that they're going to have an impact on future generations, or that they have children, or that they discover something amazing, move humanity forward, or just like you're a nice person and you're like nice things happen around you and you do some good in the world, like whatever, right? But if ultimately you extend, the future far enough, nothing you do will have ever mattered, will ever matter again. Like, that's a little confronting. And then you have to decide, is there a way to assign meaning to your life where that life and that meaning and all of your impact disappears? You know?
It's the YOLO universe. You only live once, and so you enjoy the moment, not the future.
Yeah. It's a very
depressingly finite.
Yeah, it's a very sort of like Zen kind of thing. Like, you really have to be in the moment because there's nothing else. Right? That's it. That's what you got.
All right. Well, thanks, Katie. Let's see if there's some other possible features of the universe that are more cheerful.
Well, more cheerful. I mean, the thing, it doesn't end well.
I don't think that there are any more cheerful ones, by the way. Yeah, that's a rhetorical. I'm setting you up for failure here. Sorry.
Yeah. I mean, that's it's never a happy story, but there are more dramatic ends of the universe. So the heat death is the sort of standard picture. If dark energy is something other than a cosmological constant, if it's something that changes over time, there's nothing to say that it doesn't turn around and go from doing expansion to, sort of contracting. And if that's the case, then we can end with a big crunch.
Mm-hmm. The opposite of the Big Bang.
And so that would be where the expansion would at some point stop, turn around, and everything would come together again. And that's a really exciting one because, the galaxies would all get compressed and like start interacting with each other, merging, and then everything gets just more and more dense, more and more crowded. And the cool thing about the Big Crunch as an end of the universe scenario is that it has this really neat feature about how the stars die. So you would think, like, you have a whole bunch of galaxies colliding with each other, the stars would collide and blow up or something.
Yeah.
Right? Like, that's what you would imagine. But actually, when galaxies collide, the chance of stars individually hitting each other is tiny. Like, even when we're going to collide with Andromeda in 4 billion years, the chance that any single stars hit each other in that collision is vanishingly small.
Space is very big.
Space is huge. Yeah, and even when galaxies are coming together, space is huge. But in a Big Crunch universe, the space is compressing not just the matter, but also all of the radiation. And so, there's this cosmic microwave background floating around from the Big Bang, that energy will be compressed again to, the energy density it was in the early universe. And so we'll start to get to that hot plasma stage again. But even worse, in the time since the Big Bang, we've had all these stars shining. So there's all this higher energy radiation floating around, X-rays and UV and visible light. And that'll start being compressed as well. And so we'll be cooked by this radiation background from all the starlight, from all the stars that have ever shone. And then at some point it gets so compressed that the surfaces of stars catch fire. They have thermonuclear explosions on the surfaces of stars.
As opposed to the middle of the star where we now have them.
Yeah. So stars will start to be cooked from the inside out. And at that point, like, nothing is survivable. That's it.
So the Big Crunch is not just the Big Bang run backward in time.
Yeah, no, it's worse.
Not the time reverse.
Yeah. It's actually worse than going back to the Big
The question is, is it better to burn out than fade away, right?
Right.
Either way, your goose is cooked.
Yeah.
But in the heat death,
yeah,
you slowly slide into oblivion.
Yeah.
And in the crunch, you get roasted to death and you burn.
Yeah.
And you can predict, when it's going to happen, right? Like
Yeah.
if the universe were collapsing through general relativity, we could be able to say exactly how long we have.
Yeah, if we had measured a really high deceleration parameter, we would have a date, we would have a number for how quickly that's going to happen. And I feel like that would be kind of a terrifying concept.
That's way worse than heat death in my mind.
Yeah. I mean, I guess the one thing that people find some hope in is that sometimes some of these big crunch models have a bounce. So where there's a big crunch and then there's a new Big Bang afterward. Again, not our universe. Like, we're still done. But
so
some
even
people
if we
like
bounce
that
into
idea.
something, you're saying our universe can bounce, but there'll be no
gone.
record of us.
Yeah, exactly. Yeah.
We have no way of sending books through the bounce.
Nope.
Or CDs.
Nope.
Whatever, podcasts.
Yeah. I mean, I can get to it later. There are some models of a bouncing universe where you get a little bit sort of surviving through the bounce, but this one where you'd have a big crunch is not one of them. So there's the big crunch, and there's also another way that dark energy can go wrong that can give you a different end of the universe, which is something called phantom dark energy. So and this is theoretically a mess, and I know you don't like it, but I
have my opinions. That's okay. It's a free country.
Yeah, I mean, but it's a cool idea. So, like, the regular cosmological constant has the density the same everywhere all the time. If you have something called phantom dark energy, the density of the dark energy is increasing over time. And what that does is it means that suddenly the dark energy is able to not just move galaxies apart from each other, but start pulling galaxies apart themselves and ripping stars off galaxies, ripping planets away from their stars. And so as the density of dark energy increases and increases over time, you get to a point where it rips the entire universe apart. So first it gets the clusters of galaxies, and then the galaxies, then the planets, and then, atoms, and then the whole universe is just rent asunder. And that's called the Big Rip.
This also sounds bad.
Yeah. Yeah, and this is another one where it would be terrifying because we could predict it. Like, if we measured a certain kind of dark energy, like, we would have a date. So there's a parameter that we measure for dark energy now called the equation of state parameter. We call it W, and it has to do with the balance between the pressure and the density of dark energy. And right now we measure it looks like it's exactly -1 or very, very close to it. If it's a little less than -1, then that's phantom dark energy, and that leads to a big rip. And once you know the number, what that W is, it tells you exactly how many years you have till the big rip happens. And right now, the data are consistent with W equals -1, but the best fit part of the data, like the number
W equals -1 is the constant energy.
That's constant. Yeah, that's the cosmological constant.
Yeah.
But the best fit measurement right now is just a little bit less than -1.
Well,
but the error bars are so big, like, we really have no idea.
Let's not alarm people too much.
Absolutely. Yeah. No. But you can calculate like a maximum, like a minimum amount of time our universe has within the data, the errors of the data. And so we know that we have at least 120 billion years. And so, probably, and like as we measure closer and closer to W equals -1, if that's what it really is, that number will get higher and higher. And so, right now we have at least 120 billion years. With the next experiments looking for, measuring W, maybe we'll get to I don't know, 500 billion years or whatever. So presumably, if W really is -1, if we really live in a cosmological constant universe, we'll just keep pushing that doomsday farther and farther back.
Yeah.
But it's a neat idea that you can calculate it exactly if it's out there. Now, your objection to phantom dark energy is that theoretically it's a mess.
Yep.
Right? There's like it breaks energy conditions. Like there's a reason why you shouldn't have dark energy increasing in energy density everywhere all the time. Bad things happen in the theory. But I kind of like the idea that you can extend the parameter space of your model just a little bit and destroy the universe.
And it's worth mentioning that this idea that as the energy density increases, it rips apart galaxies and stars and so forth, is unique to these phantom energy models where the energy is increasing. Like the cosmological constant doesn't rip galaxies apart.
Yeah. The cosmological constant only expands really empty space. Like wherever there's gravitationally bound things, cosmological constant is not going to mess with those. Basically because there's a certain amount of dark energy in that region and your matter is already bound in that region. There's not going to be more dark energy in that region because the energy density doesn't increase over time.
If you're a regular podcast listener, then probably like me, you're a fan of audiobooks as well. And audible.com is a wonderful source for audiobooks, but also Audible originals, including documentaries, scripted shows, and things you can't hear anywhere else. I have fond memories of driving across the country listening to The Iliad and The Odyssey on audiobook, but audible.com will bring you all sorts of genres, nonfiction as well as fiction. Many of our Mindscape guests have books that also have audiobooks you can get from Audible. Recently, we listened to Melanie Mitchell talk about artificial intelligence, and her new book is available on Audible, but also Michelle Gelfond, Michael Mann, Adam Becker, and so forth. All of these wonderful authors have their books available on audible.com. So as an Audible member, every month you choose one audiobook regardless of price, as well as 2 Audible originals. Mindscape listeners get a special offer. You can start listening with a 30-day Audible trial for free. Choose 1 audiobook and 2 Audible originals, absolutely free. Visit audible.com/Mindscape or text Mindscape to 500-500. That's audible.com/Mindscape or text the word Mindscape to 500-500. You've hinted at this already, but maybe it's worth emphasizing that we're trying to experimentally distinguish between these possibilities. There's more possibilities to come, but you've laid out 3. You know, the heat death, the crunch, the recollapse, or the big rip. And we're actually trying to ask which one is real.
Yeah. But I mean, measuring how dark energy works is one of the ways. It's basically the main way that we can try and distinguish between these models. If we figure out exactly what dark energy has been doing and what it's doing now, we can extrapolate into the future to decide if we think it's going to just keep going the way it is, get stronger, or turn around, or get weaker or something.
And what are the best ways to do this measurement?
Well, again, dark energy is a tough thing to measure. So we basically can measure the expansion history or the growth rate of structure. When we measure the cosmomicrowave background, the fluctuations in this background light, we can get some hints from that as well, because it affects sort of the shapes of the fluctuations in that we see from here. So we can get some information that way. And then there are all these, experiments, like lab experiments testing alternative models. But mostly it's just really, really carefully measuring how the universe has been expanding since, early times.
And so what are the biggest experiments they're going to do this for us?
There's one called LSST, which is the Large Synaptic Survey Telescope. It's going to do a sky survey many times, observe the same part of the sky many times over and sweep the whole sky, repeatedly. And that's going to give us a really great survey of galaxies and things like that. Surveys that look at distant supernovae can tell us something about that because they can measure the expansion rate based on understanding supernovae, figuring out how far away they are, and then learning something about the expansion that way. That's one of the ways we do it. There's a couple of other telescopes that are sort of specifically aimed at looking for dark energy stuff. dark energy camera, dark energy survey, these kinds of things.
You mentioned large-scale structure. Maybe explain a little bit more how dark energy affects the large-scale structure?
Yeah, so the large, when I say large-scale structure, I mean like how galaxies and clusters of galaxies are laid out in the universe. There's this kind of cosmic web where you get clusters and you get sort of filaments where galaxies lie along those filaments, and then big voids. And if we can measure the how that large-scale structure is laid out, we can sort of extrapolate how it formed and how it's been growing over time. And so that can tell us something about how dark energy has been influencing this. Because, gravitational collapse is how galaxies and clusters of galaxies grow, but they're always kind of fighting against the expansion of the universe. And as the expansion is getting faster, it's preventing more collapse of structure. And so the shapes of and sort of statistics of large-scale structure can tell us a lot about what's in the universe and how it's changing over time.
So it's like throwing a bunch of baseballs up in the air and seeing which ones fly away and which ones come back to the
It's like it's like if you're trying to, I don't know, if you're trying to put together a puzzle and somebody's sort of pulling the table apart while you're doing it, you can figure out so you can figure out how well you can put together this puzzle, what's going on the table. So
it certainly sounds like the dark energy is the important thing for figuring out the future of the universe.
For that stuff. But there are some caveats to that, because there's another model for the end of the universe that doesn't really have anything to do with dark energy and comes out of our understanding of particle physics. So there's something it's been kind of in vogue lately because of measurements done at the Large Hadron Collider, and this is called vacuum decay. So vacuum decay.
This is what I'm sure everyone has been waiting for.
Yeah, vacuum decay
is the coolest part.
This is the absolute best. Most interesting way for the universe to end. So I'm just gonna start with the standard model of particle physics. So the standard model of particle physics is our encapsulation of all of the particles of nature and the forces of nature as we understand them through experiments. Okay, so we have a certain collection of particles. We have quarks and leptons, and we have these gauge bosons, which are force carriers. And so there are all these particles that we understand, we've measured, and we know how they work, and that constitutes the standard model of particle physics. And the sort of final piece of that standard model was the Higgs boson, which is discovered at the Large Hadron Collider in 2012. And that tells us something about how particle physics changed in the very early universe and gave us the sort of nice, happy universe we have today, where we have, atoms can come together and form molecules chemistry and so all of that works because of what happened with the Higgs field, this sort of energy field pervading space in the very early universe. And the Higgs boson is an excitation of the Higgs field. It's a little sort of piece of that Higgs field that we can break off and examine with our colliders. So
interested listeners can buy a book about that I wrote. So
right, exactly, yeah. And so once you have the whole standard model of particle physics and the Higgs boson part of that, you can start to kind of examine how that mechanism happened and whether it happened in a way that gave us a really stable universe or not. And so you can kind of chart out based on the masses of the Higgs boson, the top quark, where we lie in this landscape of stable universes or not stable universes. And when I say stable, I mean a universe where it's pretty much the workings of particle physics are expected to just stay the same forever.
Forever, yeah.
Or you could have an unstable universe where it would already have destroyed itself, it already wouldn't work at all. Or you can have what's called a metastable universe, where particle physics is fine for now, but eventually it's all going to fall apart. And
you have to tell us more about what does it mean it's all going to fall apart.
Yeah, so what I mean by that is, so I have to say a little bit about the Higgs field. So the Higgs field is this sort of energy field pervading space, and particles interact with the Higgs field, and that kind of determines the mass of particles. Okay, so an electron or whatever interacting with the Higgs field interacts with the Higgs field a little bit, so it has a little bit of mass. A quark, top quark or something, which is quarks are constituents of protons and neutrons. Top quarks are not part of protons and neutrons, but they're cousins of the ones that are. That one interacts with the Higgs field in a slightly different way. It'll have a higher mass. And so there's something about particles interacting with the Higgs field that tells you something about the masses. But the Higgs field itself can change over time. And the value of the Higgs field, sort of the amount of energy in it, has changed since the very early universe.
Right. So it's just not just hypothetical that we think it could change. Yeah. We think it really did change.
It did change.
The Higgs field had a different value early on.
Yeah. And so the Higgs field had a different value early on, and now it has a certain value that we can kind of measure. And it's possible that there's another value it could take that would be somehow energetically favorable. So the way people usually draw this is like, you have like a valley and you have like a ball sitting in a valley, and that's pretty stable. But if that valley is not really a valley, it's just a little sort of divot in the side of a much deeper valley, then your little pebble or whatever can sit in that divot. But if something kicks it a little bit, it can fall off and end up somewhere else in this deeper valley. And that deeper valley would be the stable state. And this little divot that's higher up is less stable because it's energetically favorable to like give it a little push and then it falls down and it lands somewhere else. Kind of like if you have, a cup of tea right at the edge of a table, it's sort of stable, but if you tap it a little bit, it's going to fall down, it's going to hit the ground, and that's where it's really stable. So you want to put your tea on the ground, or you don't want to put it right near the edge of a table.
But you're saying the Higgs field had its current value for something like 13.8 billion years,
yep.
But nevertheless, it might be temporary.
Yeah. So it's possible that, we're not like right at the edge of the table. Our teacup is in the middle of the table, but there's still room for it to fall
There's a chance.
off. There's a way it could fall off. And in normal life, if you have a teacup in the center of your table, you're probably it's not gonna end up on the floor unless you do something really dramatic and knock it over. But unfortunately, the universe on the scale of like fields, like the Higgs field, is fundamentally quantum mechanical. And with quantum mechanics, you get quantum tunneling. And so we live in a universe where it's very unlikely that anything could actually move the Higgs field to this other minimum, if that minimum does exist. But if you leave it alone long enough, it could tunnel right through and end up in the other minimum. It's like if you had I'm going through tons of analogies here, but
please, no, that's helpful. Yeah.
Like if you have this pebble in this divot on this valley, in this edge of this valley, something could kick it over, but imagine that like it would take a lot of energy to kick it over, but imagine also the edge of that divot is kind of soft and it could kind of fall through, and then it'll just end up rolling all the way down and ending up at the bottom of the hill. And this is, at the face of it, maybe this doesn't sound so bad. We don't know what the Higgs field is doing in our daily life. Like, what does it matter what the strength is? Well, it turns out that if you change the value of the Higgs field, you change fundamental constants of nature in such a way that atoms don't hold together anymore.
No more chemistry, no more
no
life.
more chemistry, no more. Yeah, everything is terrible. And then also, if it does go to the Higgs field goes to a much higher value, then in some sense, like everything gets more massive, and then you can have a gravitational collapse of the entire universe once that happens.
That sounds bad.
Yeah. And so it's not a good thing. So we don't want to end up in that other minimum of the Higgs field. That's called the true vacuum. We apparently live in a false vacuum. So it's called a false vacuum because it's not like the real vacuum state of the universe. It's not the
once
real
and for all true final.
Yeah.
So,
yeah.
But wait, you say so. Just to be clear,
yeah.
You're saying that not only is it conceivable that there is another vacuum state where the Higgs field has even lower energy that it wants to go to, but that we think it's true?
Yeah. The experiments, the data point to the probability that there is another vacuum, that we live in a false vacuum, and that there's a true vacuum out there in theory where our Higgs field could quantum tunnel into the true vacuum.
And does the tunneling happen all at once all throughout the universe? How does it
No, it's a cool thing. So it's a very low probability event. Like any quantum tunneling event, it's not likely to happen. But if you leave it alone long enough, eventually it will. But the way it would work is, we have Higgs fields throughout all of space, and at any point in space, the Higgs field could quantum tunnel to the true vacuum at any moment. with a very low probability.
Mm-hmm.
And what would happen is if the Higgs field does tunnel at one point in space, then as soon as it tunnels there, it'll kind of knock all of the Higgs field around it into the true vacuum as well. And then there'll be this expanding bubble of true vacuum. Now, true vacuum is a space we cannot live in, to be very clear. and as this bubble expands, it has a sort of bubble wall that's this high energy sort of shell. So that starts incinerating anything it touches. And then once it passes over something, whatever it passes over ends up inside the true vacuum where it can't hold together and maybe collapses on itself.
Right. Either explodes or collapses.
Yeah.
It's not going to stick around.
Yeah. So this bubble then expands at likely about the speed of light, or very close to the speed of light, and expands through the universe and just destroys absolutely everything. And so because it's happening at the speed of light, because this bubble is expanding at the speed of light, you absolutely cannot see it coming. So if it were happening, if it started on the other side of the room, by the time the light gets to you from the bubble is on top of you and is eating you up. So you can't see it coming. Fortunately, you also wouldn't feel anything because your nerve impulses do not travel at the speed of light. So you won't have chance to feel it hit you. But it would destroy absolutely everything. And it could happen at any moment, technically. I mean, it's very, very unlikely. But, the Higgs field in this room, there could be a quantum tunneling event right now that would create this bubble of true vacuum and just destroy everything.
And we mainly know that it's unlikely because it hasn't happened yet, right?
So it hasn't happened yet, but also we can try and measure the parameters of the Higgs field in such a way that we can infer that the tunneling time is very long. And so, estimates I've seen give us something like 10 to the 100 or 10 to the 500 years before it's likely to happen in our observable universe. So, that suggests that by the time this is happening, we probably don't care. We're sort of well on our way to the heat death. Probably it doesn't make a big difference. But one thing that I've been working on recently is there's this calculation that was done by a few others that showed that if you have a very small black hole, as it's evaporating, it can trigger vacuum decay. So it can basically, in its vicinity, so a little black hole, as it's evaporating, can make the probability of tunneling in its vicinity much higher. And so if you leave a black hole alone long enough and let it evaporate all the way, then it can make vacuum decay happen. It can seed that event. And we know there are lots of black holes in our galaxy. And eventually, as the heat death is progressing, those black holes are going to stop pulling matter in and start just evaporating. And so if you calculate the lifetime of our observable universe based on the black holes we know about evaporating, we've got only much less time. So I mean, it's still something
a
like
lot of time.
It's still something like 10 to the 69 years, and we're not fully sure that black holes can do this to the vacuum. We're not even fully sure vacuum decay can happen.
And that 10 to the 69 years comes from imagining that we have black holes the mass of the sun or more.
5 solar masses.
Solar masses that we know about. If there are small black holes in the
small
universe,
black
it could
holes,
happen a lot faster.
Yeah. And one of the things that you can do with these calculations is you can show that, as long as vacuum decay is possible, we can't have had little black holes of a certain size produced during the Big Bang, which is something people talk about sometimes, primordial black holes.
Yeah,
and
they can't be the dark matter.
Sorry?
They can't be the dark matter, for example.
Yeah, I mean, there's caveats on that for the masses of them, and there are certain mass ranges where it's not fully ruled out. But really small ones that would have evaporated by now might have destroyed the universe, so probably they're not there.
So literally at every point in space in this universe, which has a radius of 40-some billion light years across, there's a chance, small one, that the Higgs boson field flips into some larger value. There's a bubble that expands at the speed of light and will eventually hit us and we'll all die.
Yep.
Could we hurry that up not only through making black holes, but at the Large Hadron Collider? Are we going to trigger doom on ourselves?
No, we can't do it at the LHC. So what you could imagine is if we could make a little black hole, then that thing could trigger it, right? But what we can do with smashing particles together at the Large Hadron Collider is way less powerful than what cosmic rays do in space all the time. And we've measured cosmic rays, particles like nuclei coming from distant galaxies, whatever, particles, protons, at energies so much higher than the Large Hadron Collider, we can't even come close to creating collisions that energetic. And so just the fact that those collisions are happening all the time in space and have not destroyed us suggests that there's really no possible way that we, with our little smashing of particles here on Earth, can do anything even slightly dangerous.
So there's no prospect of a Dr. Strangelove doomsday device bomb using vacuum decay?
No, I mean,
So
and I've tried. I've been talking with some colleagues about possibilities for can you do this on purpose, and it doesn't seem possible.
It's going to get you on some watch lists if you send email about these things.
Yeah. That's a maybe side topic, but yeah, I mean, as far as we know, there's no way to make a little black hole. The cosmic rays are clearly not doing it. And I actually have a paper that I just wrote about with my colleague Bob McNeese about calculating, the fact that cosmic rays are not making little black holes that destroy the universe can tell you something about higher dimensions of space, because it's easier to make black holes if we have higher dimensions of space. And so the fact that little black holes have not been created and then triggered vacuum decay can tell you something about these extra dimensions. So there are ways to use these kinds of things to think about new things in physics. But
you're making lemonade out of some lemons here.
You're
using the fact that we are still here and haven't died to constrain some parameters of the universe. Yeah,
and it's fun. It's fun to do all these what if things. I mean, it may sound like a scary thing, the idea that the universe could have this, bubble of quantum death that goes and kills everything. But
bubble of quantum death. It's a good band name, but a scary prospect.
Yeah, but it's still so poorly understood how all this stuff might work, that at the moment the best we can do is try and do some calculations, try and get something cute out of it, try and learn something from these kind of hypothetical, maybe this will happen, maybe it won't. What does that tell us? What can we extrapolate from that? I mean, and that's kind of one of the main reasons that it's interesting to think about the end of the universe, because it kind of tells you something about the assumptions of your physical model. And so if you extrapolate, let's take what we know and extrapolate it all the way to the edge of our knowledge. What does that tell us? That can either tell us something about the far future, or it can just tell us something about what kind of assumptions we're making about our model and how we can use that to better understand the physics of today. And so that's kind of fun, So this idea that, we're looking at little black holes and vacuum decay and cosmic rays and all this stuff, we're really just taking all the tools we have and trying to understand a little bit more about real present day physics from these wild extrapolations, which is it's a fun thing to do.
So there's even a silver lining on the cloud of the complete death of everyone you know and love.
Yeah, exactly. I mean, and to be fair,
the cosmic perspective is really quite useful sometimes.
I mean, and to be fair, I should say, there's really no reason to worry about vacuum decay, because first of all, it's very unlikely. Several people, say that probably it just means that we don't understand our theory. And, the idea that vacuum decay is even possible is pointing to some kind of pathology in the theory. But also, it's not like you wouldn't feel it. You wouldn't even notice it because you wouldn't see it coming. You wouldn't feel it.
Yeah.
Nobody would miss you. There's no tragic aftermath. It's
this is very cold comfort, Katie.
I mean, I don't know. I feel like there are things that we can worry about that are much more immediate and that we have some control over.
That's true, but to tie it back to something we said before, in the case of the Big Rip or the Big Crunch, we could plausibly imagine that you could predict exactly when it was going to happen.
Yeah.
One of the features of vacuum decay is you have no idea.
No idea at all.
And you would not even know that you'd made a mistake.
Yep.
You'd be here, you'd be walking to the grocery store, optimistic about what you were going to cook that night, and then you're gone.
Yeah, and that's one of the frustrating things about it, is that you don't get to find out if you're right. You can do calculations of,
That's what really matters.
Yeah. I mean, you can never publish, right?
Yeah, I know, exactly.
What's
no
the
more
point?
citation counts after the death of the universe.
Yeah.
And it's important to remember that the idea of vacuum decay, destroying the universe, this is an old idea. This was in the 1970s. Sidney Coleman and friends came up with this idea. But I just want to get across to myself as well as to the audience that there's a new piece of information now, not just that, well, maybe there are some fields out there that could decay and that would wipe everything out. But, oh, no, the fields we know about and have detected could be responsible for this.
Yeah. And our best measurements of the Higgs field, based on what we've done with the Large Hadron Collider, really point to this metastability. This idea that the universe is stable for now, but not forever. And if you leave it alone long enough, it will do vacuum decay.
And we're not sure because there could be new fields or whatever getting in the way.
I mean, that's another thing that suggests that we shouldn't worry about this too much, is that the whole idea of vacuum decay depends on the assumption that the standard model of particle physics is the whole picture. And we know it can't be. We know that it doesn't fit well with like general relativity, and like we know there's got to be something that'll replace or modify the standard model of particle physics. Whether it'll modify it in a way such as to save us from vacuum decay, we don't know. But it's very plausible that something will come up that'll change our understanding of vacuum decay in a way that will mean that, it was never a worry to begin with. But if we want to just take the standard model of particle physics fully seriously and extrapolate all the way, then this is what the data tell us. And the standard model of particle physics has been very successful. It's passed every test we've thrown at it. But just like general relativity, we're pretty sure it can't be the whole picture. There's got to be something else. I mean, dark matter and dark energy don't fit in the standard model of particle physics.
Yeah.
Therefore, there really has to be something else that
dark energy fits pretty
idea.
easily, but dark matter is definitely.
Well, dark energy. Well, I mean, if it's a cosmological constant, then it's not really part of that question. But if it's some kind of dynamical field, it doesn't fit.
But you did mention, if it is a dynamical field, you mentioned the slightly more hopeful prospect that we could crunch in some sense, but then be reborn in a Phoenix universe. We could bounce instead of just crunching.
Sure, yeah, and that's so there are several ideas that have been around for a while that involve some kind of collapse and bounce. There's an idea that was first described by my PhD advisors, Paul Steinhardt and Neil Turok, which is this idea that maybe in the very early universe, instead of a very rapid expansion, there was some kind of slow compression happening. And that could explain some of the same things that we seem to see in the early universe. And that compression was the universe getting ready to sort of expand again. And so you can have a universe that expands and then has some kind of compression and then expands again and kind of goes in and out and has this sort of bouncing cyclic nature. That model is called the ekpyrotic model, and that's been going through various variations over the years. At first, it involves two parallel universes kind of slamming into each other and then coming apart and bouncing back and forth like hands clapping. Now there's a model that doesn't require extra dimensions and other universes, but has a sort of similar compression and expansion cycle that goes on. So there are some of those kinds of models floating around that have these cycles, and in some of these models you can have something kind of surviving through the cycle, so it doesn't go completely singular, where you don't go to fully infinite density and then bounce off of that. You can have a sort of slower bounce, and maybe something interesting could go through there.
Okay, but again, just to be clear, it's not a prospect that will build a really secure safe and put some information in there instead of time capsule to the future.
Yeah, I mean, it would basically destroy everything, but you might have sort of traces of fluctuations in the matter density or something that could pass through and something like that.
So what are the chances that when we look at the cosmic microwave background carefully enough, we'll decode signals from previous universes?
Well, it depends on who you ask, because there's also this model by Roger Penrose,
previous podcast guest. Okay. Roger Penrose.
Yeah,
we talked about it.
Yeah, where he's looking for these signals in the cosmic microwave background that would come from a previous cycle, and whether or not there's been anything seen there is very controversial. Most people say that there are weird little fluctuations. They're probably statistical noise, but it's possible as we keep examining the cosmic microwave background, we might see something that indicates some previous cycle or some kind of interaction with another kind of universe. There's also a model where you have little bubble universes that start in through the inflation process, and those bubbles could collide with each other, and we could see a feature of that in the cosmic microwave background as well. So although the cosmic microwave background is really looking at the very early universe, it could tell us something about the future of the universe through giving us some insight into how our universe started and whether that's compatible with a cyclic kind of model or even a multiverse kind of model.
I'm personally not a fan of any of these cyclic models just because they make it impossible to solve the arrow of time problem. They require an infinite amount of fine-tuning in the entropy of the universe infinitely far ago. But I could be wrong about that, or maybe there's an infinite amount of fine-tuning. Who knows?
Yeah, I mean, these it's kind of, there are a lot of different ways things can go right now because there's a lot that we are sort of still not really understanding about how physics works in this very fundamental way. Because we lack a theory of quantum gravity, and because there are now these discussions going on about maybe space and time aren't really fundamental, and maybe these are just sort of emerging from from something else, something quantum perhaps, as you've been talking about. Maybe there's stuff going on that is so far out of our understanding that all of our assumptions about how universes should and shouldn't behave are just wrong.
Yeah.
And
well, for the people who are not professional physicists out there, are there prospects for getting it right? Is this just hopelessly philosophical speculation, or do you think we're actually making progress on these questions?
On the question of the future of the universe?
Well, the future and the past. Are there cycles?
Yeah.
Is there different vacua?
Yeah. So I've been going around talking to people about this for a couple of weeks or a couple of months, really, about the question of how are we going to figure this out? How are we going to figure out our cosmic model, the future of the universe? And there's not really consensus among the people I've talked to.
No.
Some people are optimistic, that we're gonna really figure it out. I was just talking with Clifford Johnson yesterday, and he's a string theorist who's worked on
previous podcast guest.
Okay,
Clifford Johnson.
Yeah.
Yes.
And he's very optimistic that we're going to figure it out, but he's optimistic on timescales of maybe it'll take 100 years. Whereas I've talked to some other people who say we just have no idea what's going on. Our experiments aren't giving us anything useful. Our observations aren't getting us anything useful, and theoretically we're stuck in the mud. I think we're in an interesting time right now because all of our particle physics experiments are fully consistent with the standard model of particle physics. All of our measurements of the cosmic, evolution are fully consistent with the concordance cosmology. Dark matter, dark energy, expansion, Big Bang. General relativity is passing every test with flying colors, but we know that those things don't all fit together in a fully consistent fundamental theory. And so we know there's got to be something. At some point, something's got to give.
Yeah.
And we don't know what it is, and we don't have any clues really pointing us in a direction to figure it out. And so maybe we just need more data, and as we get more data, we'll start to see where the cracks lie. Maybe we need an advance in theory, and maybe, better understanding something like quantum information will show us, the path to a new theory that'll tie everything together and show us how all these pieces fit. But at the moment, it's kind of all up in the air, which is interesting, because we have these models that are so predictive and so perfectly fitting the data. And we really understand very well what the universe is made of, how long it's been around, how it's evolved over 13.8 billion years. We know all that so well. We can calculate everything. We can measure everything. But fundamentally, there's something we're missing about the fundamental nature of reality. And that's an interesting place to be.
Yeah, as a scientist, that's where you want to be, right?
Yeah.
We would like more observational experimental clues.
We would we want to find something weird that we can't explain with our current models. That would be nice. And so far, there's not a whole lot of that out there. There are a couple of weird little anomalies that may or may not be telling us about new physics, but there's nothing that says this can't be explained by our current models, therefore we need to find a model that does explain it. We don't have anything like that, other than the sort of the inconsistencies between these very successful pictures that work in different regimes.
And at a more personal level, not you as a person, but we as people, look, you've been talking about timescales of 10 to the 100 years or infinity years. And on the one hand, by the way, I guess I haven't said this out loud yet, but it should, to me, it seems as if we should be very puzzled by the fact that the universe is 10 to the 10 years of the past and infinity years or 10 to the 100 years to the future. Like we live in the really, really beginning of the universe by any sensible measure. And why is that? Is there a good reason for that? I think these are cosmological questions of import.
Sure.
But the other is, does it actually affect how you go through your life? Does it affect how you think about your existence as a person or your job as a scientist when you can actually step back and contemplate the fact that in most of our sensible extrapolations to the future, no remnant, no bit of information about your existence will still be anywhere to be found.
Yeah, I mean, and I've been thinking about this a lot. One of the things that I ask when I've been interviewing people about this for the book, one question I ask everybody is, how do you feel about the end of the universe? How does that affect your life, your philosophy? And I get lots of different answers. Some people are super depressed about it. Some people find the idea of the heat death super boring and they're desperate to find something else. Some people are totally cool, like Zen, like living in the moment, whatever. It's great that we don't last forever. For me, I think that I find it a little troubling, the idea that we have no legacy. Like I find that a little bit hard to think about without feeling sad. But I also find that having my head in these clouds all the time, but not, it's not head in the clouds in terms of something, inconsequential. Like this is real physics, this is actual universe that I'm thinking about. So that, it's removed from me, but it's not imaginary.
Yeah.
I do find that there's a sense in which it's kind of comforting. Like when I think about like my little problems in my little life, the universe is going to end. Like, like what does it matter?
Maybe before this grant proposal deadline.
Yeah. So it sort of does put some things in perspective. I mean, and even the idea that we have no legacy ultimately. Like I experienced a loss in my family a little while ago, and part of sort of the grieving process, I was thinking about that she's gone, and that was really sad. But I also thought, well, we're all gonna go eventually. Even the whole universe is gonna end. The important thing is that we make the most of the time we have. I spent quality time with my grandmother while she was here, and now she's gone, and it's just like in the universe, we can spend quality time with our universe now, and eventually it'll go away, and that doesn't mean it's meaningless. I think even if it's gone, there's still some meaning that it was here, that we were here, that we as thinking beings figured some stuff out. I think that's still a meaningful and important thing.
I cannot even imagine anything to add to that. Katie Mack, thanks so much for being on the podcast.
Thank you for having me.